and welcome to this third session, the third exercise, structural analysis with Robo Structural Analysis Professional. Um, on the third exercise, this is what we shall be doing. We've done this on the first, this on the second, and this on the third. I want to recommend something at this level. Please do not feel like there are concepts that you already know. So you've watched the first exercise, the second exercise, and you feel like you already master a lot of concepts. You have to follow along with every single exercise if you want to master all the complexity and the flexibility of this software when it comes to analysis. So on every single exercise, we are adding a new concept. We are adding some new explanations that enable you to understand the software better. So don't neglect any part of it, please. Okay. So this is the exercise that we have as challenge today, and the question is determine the reactions at the support. We have just one beam. It is pinned at A and roller inclined at B. But the inclination here is quite interesting, right? So we have a perpendicular line here to the normal inclination, and it forms an angle of 30 degrees with the horizontal. So it implies that the roller itself forms an angle here of 30 degrees with the vertical, right? So just take some time and analyze that. Is but logical, okay? It's as if you take this and then you rotate it, and you will see that the inclination this way, right, corresponds to an angle of 30 degrees with the vertical. So that's the way we will interpret it in order to do this exercise correctly. Okay. So now let's go ahead. We have a triangularly distributed load here from 0 to 6 feet, and from 6 feet to 18 feet, which is a distance of 12 feet, we have a uniformly distributed load of 5 kips per feet, and from 18 feet to 24 feet, which is a distance of 6 feet, we have a triangularly distributed load again, which is quite symmetric and opposite to the first one. Okay, so let's try to model this in Robo. So how are we going to go about this? Um, the very first thing I'll recommend that we do is to make sure that our units are okay. I can see here feet, it means that it's already imperial units, but let's first of all start by opening a new file here, and we'll take 2D frames. Okay, so we can see here that the measurement is already in feet, but just to be sure, we'll go to tools and make our job preference to be imperial units, right? So we are sure. Good. So with that, I'll set up the grid system to correspond to what we are having here. Okay. So we are having our distances to be multiples of 6 somehow. So if I set my grid system in the x direction to be 6, then I think we can model very, very easily, right? So we'll go to view and grid, and grid steps. So it is 10 here, but on X we want it 6, and I'll also put it on Y6 just for the sake of having a square grid system. Okay, so I'll apply that and close, and we can zoom to a certain level, and why not start at 0 here? Okay, good. So now that we're there, we can draw our beam. Okay, so we'll go to click on the bar. Again, we are calculating reactions here. So the simple bar here, the type of bar doesn't matter. The section does not matter. Okay, all we need to do is to draw our bar normally. And I would like to draw it somehow differently this time. Okay, somehow differently. I would like to draw the bar this time without clicking on the drawing area, just indicating the coordinates right here. Okay, so we would like our bar to start at coordinate 0 following x comma. Okay, let me do something here so that you understand what we are talking about. So when we move the bar here, what will you notice? You'll notice that here, um, every coordinate is recorded. Okay, it follows our mouse and then records the coordinates of where our mouse is currently located on the drawing area. So what is written here is x, the coordinate following x, comma the coordinate following z. Okay, according to what we have as our reference down this way. Okay, so if we want a straight line, if we want a horizontal line, it implies that the coordinates following x have to be the same, no matter where it appears. Okay, so we will start at 0 for y, comma 0. That will be our initial point for the first point of the beam. Enter. Enter. What's happening? Okay, I've indicated 0 0. Okay, that will be that's the beginning coordinate, right? So the ending coordinate now I can also indicate that, and then we'll just click on add and everything will be fine. So if I've indicated 0 0 as my beginning coordinates, you can now see on the drawing area, right, that a line is being drawn from that point. These are the coordinates here: 0 this way and 0 this other way. So what will be the ending point? Well, the overall distance of the beam according to the exercise is 6 plus 12 plus 6. That gives us 24, right? So we want it to be 24 comma 0, right? Because the distance is measured in the x direction. Okay, we need to have a constant z value if we want it to be horizontal. Okay, so we'll just click on add, and we should have our bar, which is right there. Okay, so to be sure about that, we can always go to tools and go to dimensions and measure it to be sure that it is 24, right? If I click right here and go down, okay, so you can see that it is actually 24. Perfect. So that adds another flexibility. I hope it's a different method compared to what we've used so far. Okay, so the next thing I would like us to do is to model the loading. Okay, so the loading has to be done differently this time around. Okay, we have a triangularly distributed load on this side from 0 to 6, a uniformly distributed load from 6 to 18, and we have from 18 to 24 another triangularly distributed load, right? But if we've understood everything that we've been doing so far, it should be quite easy to model that. So we'll first of all have to go ahead and define and add a particular load type. Let's add it as a dead load. It's under the dead loads that will define every other load. Okay, so we'll close this and go ahead and define our load properly. So the type of the load will be the bar. Okay, we want it to be trapezoidal, right? Because trapezoidal is the way we can easily draw triangularly distributed loads. Okay, so when I click there, this is what we have. Okay, so according to our exercise, okay, the first load on P1 has to be 0 and P2 has to be 5 kips per feet, right? That's what we need to have. So what are we saying? At P1 we want 0 and at P2 we want 5. Okay, or rather in our case -5. It is following the z direction, right? But it is opposite to it, so we want it downwards, not upwards. Okay, now at the level of coordinates now, this is where, or this is a part where things may be a little bit different. From exercise 1 and exercise 2, we've always been using relative coordinates, right? This is a case where you want to use absolute coordinates. Now, in absolute coordinates, you represent the exact distances of where the loads are being applied, the exact distances. You don't represent them in terms of 0 and 1. So in absolute, 0 will mean 0 feet and 1 will mean 1 feet. In relative, okay, 0 is 0 and 1 is the overall distance. It's a measurement of L divided by L. It's a comparative measurement, okay? So in absolute, it is the exact distance that you're representing. And here we need to represent the exact distance. We want it to go from 0 to 6 feet. Okay, so it is not that we cannot use relative here. We can still use relative, and but using relative here, or maybe we should go ahead and model it in the two different ways. Okay, let me use absolute first, then after that we'll use relative. Okay, so let's go ahead. For absolute, x1, which is this distance, because it's a triangularly distributed load that we want to model first, x1 here will have to be 0 because it starts at the beginning, right? At the beginning of the first node. And then x2 will have to be 6, okay? Because that is where P2 is found at a distance of 6. Okay, so if we add that, okay, remember the orientation of the arrow matters. Okay, this arrows implies that we are moving from node 1 to node 2. So this is where we want to click to have the triangularly distributed load. Okay, and the system is symmetrical. It implies that if I come this way and this arrow is instead showing the other direction, then it will consider this as node 1 and the other part as node 2. That's what I want also, right? For the opposite, since it's symmetrical, so it will just draw the triangle in the opposite direction, and that's exactly what we are looking for. So when I click here, the triangle appears on the other side. So what is left here? What is left here is just a uniformly distributed load in the middle here, right? So you may tell yourself that we have a particular button here to model the uniformly distributed load. So we just go ahead and we can implement that. The problem here is that we have just a single beam, okay? And the uniformly distributed load here does not offer us the same flexibility that the trapezoidal load offers. Here, when we model the uniformly distributed load, it can only be applied on the overall length of the bar. Okay, but in this case our uniformly distributed load is not applied on the overall length of our bar. It is applied from 6 here to 18. So how can we go around that? The first way we can do that is to model this particular beam as three different elements. So one beam that goes from 0 to 6, another beam that goes from 6 to 18, another beam that goes from 18 to 24. So that when we are applying this load, we can just go ahead and click on this middle beam and everything will be fine. But we did not use that approach, right? So the other approach that we will be using is still to take a trapezoidal load, but make sure that the value of P1 and P2 are the same. If the value of P1 and P2 on the trapezoidal load are the same, then we have a uniformly distributed load, right? And then we can indicate X1 here to start at 6, and then X2 to start at 18. That's quite simple, right? Good. So P1 will say -5 and P2 -5. That's the load of the uniformly distributed load right here. But X1 changes, right? We want X1 to start at 6 and X2 to end at 18. Okay? So remember, we are measuring all of these things from node 1, okay, of the beam, according to our diagram that we have right here. It's just following this picture, that's all. Nothing complex. So when I click on add, if I click right here, you see the uniformly distributed load in the middle. Okay, so that was great. That was great. But now let's do it all over, but with relative positions, no longer absolute. Okay. So for that, I'll go and delete these loads. We'll go to loads and look at our load table. And okay, and just delete everything. Okay, I press Control X. It was already selected. When it's black, it's selected. Okay, good. So it means if I display the load here, we have no load. That's okay. So let's go and define the loads again. Okay, we'll go to trapezoidally distributed, and let's start with a triangle. So I have 0 P1 and then -5. The magnitude does not change, right? But the position now, we want it relative. So relative position measures the actual position that we want to have divided by the overall position of the beam. Okay, as you can see here, it is x divided by L. So when we are looking for x1, x1, for example, in our case is 0. It will always be 0. 0 divided by any number gives us 0. But x2 here is 6, right? It's supposed to be 6. Okay, so if I come here, it's at a distance of 6, right? So what do we do when we're in the relative position? We have to divide that 6 by the overall length L. The 6 here stands for our x, and we have to divide it by the overall length x, which L, which is 24 in our case. So 6 divided by 24, that should give us something like 1/4, and 1/4 is something like 0.25, right? So if I add that and I come right here and click, then you have that triangle, and here again and click, you have that triangle. Okay, and for the uniformly distributed, we'll just say -5, and it starts where at 6, which is 0.25, and goes right up to 18. 18 divided by 24, that should be something like 3/4, and the 3/4 should give us something like 0.75, right? So if we add that, we apply it, you see the uniformly distributed load in the middle, right? That's quite simple. And if you doubt that, we can always take the measurements to be sure that we have that accurately. Okay, so let's go ahead on tools and dimensions, and from here to here, right? We want to know what's the dimension there. You see it's 6, and then from here to here, what's the dimension there? 12, right? And from here to here, what's the dimension there? Perfect, right? Just what we need. Okay. Mm, we can delete this part. Okay. I hope you know the modes of selection in Robo. If I select from right going leftwards, right, it forms this particular bluish dashed rectangle, and this particular selection will select every element that it touches. It doesn't matter if the element is completely found in the selection or not. Anything that it touches will be selected. So because all of these dimensions are touched by it, they will all be selected. Okay, as opposed to the other selection mode, which goes from left to right, okay, which is blue but not dashed, okay, solid lines. If I release this, they will not be selected. Reason being that this selects only all of the elements that are completely found within the rectangle, within the area of selection. Okay, so we'll look at that more detailing in a different example, maybe where we'll be dealing with frames. Okay, good. So we can delete this, and to delete, you just press delete on your keyboard, and that's that. So the loads are okay. We can even put the values. Yeah, they are okay. So the next thing we want to do now is to represent the support, right? The support, we have a pin support at A, and we have a roller support at B. A roller inclined support, right? Inclined at an angle of 30 degrees to the vertical, not to the horizontal. So how do we go about this? We'll click on support normally, okay, and here we are. We already have the pin support right here. We can just apply it to the first node as we saw, okay. But now the problem is, how do we create an inclined roller support? Wow, well, that's quite easy. Okay, you just have to come and click on new as usual, okay, and let's call it roller 30, to say it's a roller that is inclined at 30 degrees. Okay, let me say roller 30Z. Okay, to say the 30 is measured from the Z axis. Okay, so look at this diagram here. Robo gives you a very good indication of what you are supposed to notice. Okay, this here shows you actually the support itself. This is the bottom of the support, and this is the top for the vertical support. Okay, and here this is the bottom and the top for the horizontal support. So this actually is the part, or are the parts that will be in contact with your structure. Okay, so what does this mean? This is what we want to incline in this direction at an angle of 30 degrees. Okay, so we'll remove ux first because we don't need that. We need just ux. We need just the vertical direction to be restricted. Okay, and this has to be inclined at an angle of 30 degrees. The clockwise direction in Robo is what is positive. So to have an angle of 30 degrees in the anti-clockwise direction, we need to indicate it as negative 30. Okay, so you have direction here that is where you can incline your support. So if I put here negative 30 and I say okay, you see that it has been inclined at an angle of negative 30 to the vertical, which is exactly what we need. Okay, so we'll go ahead and add that to our repertoire of supports, and then we can, it's already selected, we can just go ahead here and apply it on this node right here. Okay, does this not look exactly like the exercise? It does, right? So I think we finished with everything here. The only thing left to do is to calculate. Okay, so you just click on calculate and you allow Robo to perform its usual magic. Okay, so what is the exercise again? uh it says determine the reactions and the supports. So what do we do? We just go right ahead on results, click on diagram for bars, and at the level of reactions, we activate. We want to see all the reaction, fx, fy, my. We want to see everything with the descriptions, right? And we can apply that and then close. So what do we have here? At the level of the first support, we have fx to be 25.98, fz to be 45. At the level of the second, fx. So you see that here it represents the components of the inclined force, the inclined reaction. Okay, it represents its fx components as negative 25.98 and its fz components as 45. Okay, so now as usual, let's check with the book to check if our result is actually correct. So that's 219. At the level of the answers, what do we have? Okay, we have FB, which is represented here as just one false, the reaction at the level of B, to be 52. But if we want to know if we are correct, then we need to calculate what the components of this FB and see whether it corresponds to what we are having here. Okay, so if it is inclined at 30 degrees here, then the component that closes the angle, which is cos, is the vertical component, right? And so FZ here is supposed to be 52 cos 30 degrees. Okay, so I open MATLAB here for us to check whether it is actually correct. Um, if we say 52 times cos d of 30, what is the answer? Perfect, it's 45, right? So it means that there is a great chance already that our component is 52, but we need to check the other component also to be sure that it's still the case. So it means the resultant component will have to be something like 52 sine 30, right? So 52 times sine d 30 gives us 26. 26. Here we have 25.98. Therefore, it's 26, right? Very, very correct. And what about the reactions at A? Reactions at A, we have 26 and we have 45. Okay, so 25.98, assume 26 because numerical calculations we have a negligible margin of errors that can occur, right? So 25.98 is truly negligible, so that's 26, and here we have 45, so perfect. Okay, so that does that. Okay, so I hope you learned a lot on this particular exercise, and see you guys on the next exercise. Bye bye.